Hello everyone, my name is Pelin Yıldırım. Today I'm going to be talking about a brief overview of quantum hardware. This is an undergraduate research project. The talk is going to include some examples of certain qubit structures. Then I will demonstrate the functionality of particular superconducting qubits, and we will finish with a conclusion. At first, why are we building quantum computers? As we all know, classical computers are not enough for complex problems, such as factorization. If the computational power increases with the quantum computers, it will be stimulating for other disciplines too, such as chemistry or finance or etc. Quantum computers use two very important quantum mechanical effects to store information: entanglement and superposition. Entanglement will be crucial for cryptography, and superposition makes it possible to have values other than 1 or 0 only. Okay, but how can we build it? Like classical computers, quantum computers also consist of many pieces. Quantum chips refer to qubits, which is similar to transistors in today's electronics. Quantum to classical part is new here. It is to transform the information into a form that the qubits can understand. For example, from a voltage pulse to a photon, depending on the qubit structure. One layer above is microarchitecture. This layer represents the interconnections of qubits. We will be focusing on quantum chips today. Challenges in building quantum circuits. First, we ask the question, what qubits are made of? This is the crucial question in qubit hardware. We have many options, some of which are real atoms and some are artificial atoms. Artificial atoms are engineered quantum systems. They both have pros and cons. Real atoms have perfect quantumness, meaning that their energy levels are convenient for qubit bits. However, we need some manipulations for artificial atoms, which we will discuss later. On the other hand, controlling the real atom is usually harder than controlling the artificial one. So we are facing a trade-off here. Let's talk about our qubit. The qubit has to be consisted of two levels, each corresponding a bit. If it is not, then we also manipulate it. Some examples for physical systems are trapped ions, nuclear magnetic resonance, electrons in solid states, etc. Okay, now we can start with topological qubits. Topological qubits use Majorana bound states as their bits. A Majorana fermion is a particle which is its own antiparticle. These particle and antiparticle also have opposite energies. Majorana fermions are good candidates because they are spatially separated. This makes the system sheltered against perturbations. Thus, coherence is longer. This is crucial for a qubit since it's a measure of the capability of storing the information. Experimentally, Majorana fermions can be found in S-wave superconductors using a nanowire. Let's move on to spin qubits. As the name suggests, spin qubits utilize spin state of the electron as its bits. They can be thought of as transistors with only one electron, where the gate voltage controls the particle. Therefore, it's not possible to talk about a continuous current flow as in the transistors today. The electron is trapped in the quantum dot. In order to minimize the fluctuations to be able to control the electron, the thermal energy must be neglected. Therefore, operation has to be done in low temperatures, only about a few millikelvins. We also have perturbations in this qubit. To be able to protect the spin of the electron, other effects must be minimized. These effects may be nuclear spin, etc. Therefore, experimentally, it is reasonable to spin-free isotopes. Now let's look at the readout of the spin cluster. An initially empty quantum dot is here, and this is the reservoir, is filled with an electron which has unknown spin. This is done by changing the gate voltage so that the energy levels are lowered, and any electron can get in, regardless of its spin. So there are two possibilities. It's either a higher energy spin, or a lower energy spin. Then we again change the gate voltage just a little, that the lower energy spin gets in. So the Fermi energy is between the two energy levels. So a lower energy spin gets in the quantum dots if there is not electron with the same spin in the dot. Because of the Pauli exclusion principle, if there's already a lower energy spin electron in the dot, then another one cannot get in. So this way, we can understand actually which spin state the electron was at the first place. This method is called Elzerman readout. Now let us move on to the Nitrogen-Vacancy center qubits. NV center qubits are very similar to spin qubits. Instead of spin qubits in semiconductor, now we have NV centers in diamond, meaning that our electron is in the vacancy of the diamond. Two advantages of this qubit are that it can operate even at room temperature, and it has long coherence time. Also, the electron in the vacancy can interact with a photon. This is very good news for quantum networks. Thanks to the entanglement of the electron and photon, distant centers can talk to each other. Here we see that a photon entangles an electron in an NV center, and here a separate photon entangles a separate electron, and when these two photons are entangled at the beam splitter, the information is shared. This is how quantum networks works for NV centers. Now we continue with our last type of qubits, superconducting qubits. Superconducting qubits are very similar to CMOS technology in terms of the fabrication process. They are built on silicon or sapphire bases. As in the spin qubit case, they operate at low temperatures. However, in contrast to other systems covered, superconducting qubits have many energy levels, not just two. Then we have to find a way to restrict higher energy levels. That's where the Josephson junctions come to rescue. Josephson junction can be thought of as a kind of inductor in terms of the energy levels. This is the energy levels for a Josephson junction, and this is for an AC oscillator. So we see here the main difference is the unequally separated energy levels. And that's just what we want. Thanks to the nonlinear nature of Josephson junctions, we do not have to worry about if an energy of E01, for example, will excite an electron in the first excited state. Thus, the main goal here is to prevent the leakage to upper levels, and Josephson junction can do this. As mentioned before, this superconducting qubits technology is very similar to CMOS. This is a great advantage for a brand new research field. However, the operation temperature is not suitable for room temperature for now. When the coherence time is considered, each superconducting qubit is unique. For example, transmon is good enough, whereas CPB is not doing well, actually. So this takes us to the family tree of superconductors, superconducting qubits. Now here we see a general qubit structure, superconducting qubit structure. It has capacitor, it has Josephson junction, and it has inductor. Here we see a classification in terms of the energy levels, energy ratios among the components. The energy ratios among the components are defining features of these qubits. For example, the difference between Cooper pair box and transmon is the EJ to EC ratio, the Josephson junction energy to capacitance energy ratio. As EJ over EC increases, we get a better performing qubit. As I said, transmon is better than Cooper pair box. So let's look at an example comparison of two superconducting qubits, Cooper pair box and fluxonium. These are the circuits and these are the corresponding Hamiltonians. These graphs are generated by my supervisor İlke and me. Here we can see the energy levels of the two qubits. But why do we care about it? As their parameters change, the circuit parameters change, the graphs change. And our main goal was to observe this change. So we generated a Python code that solves the Hamiltonian, the Hamiltonians on the previous page, to demonstrate the operation of the circuits, so that we could decide which one is better for which operation, which application, for example. And in conclusion, the main takeaway of this presentation is the most important features of a qubit are quantum nature, coherence time, and entanglement. Here today, a small group of qubits are introduced. There are many other physical realizations, as said before. We choose the qubits considering the application we will use the qubits. In order to determine the most suitable structure to realize quantum circuits, comparative analysis need to be pursued. Our aim is to contribute to developing robust roadmap of quantum circuits by performing physical and computational performance analysis. Thank you for listening.